All right, Integrated Math 3, this is the answers for, I'm going to do two lessons in one here. So it's going to be 4.01 and 4.02, and we'll go ahead and do that. All right, so what I'm going to put, we're dealing with logarithms and exponentials, and I'm going to always include this cover sheet of the basic properties and principles and relationships for those subjects. So what is an exponential? An exponential is, it's an equation where the variable is in the exponent. So instead of x squared, which is not an exponential because x is the variable and the 2 is the square is in the exponent, this actually has the variable in the exponent. That's an exponential. The inverse of an exponential is a log. And so the inverse of this would be log base 10. And if we said this equals y, that 10 to the x equals y, then this would be log 10y equals x. And that's an inverse. What is an inverse? Let's remind ourselves. So inverse is a function, is a mathematical operation that reverses another operation. So if I say 2 plus 5 equals 7, and then 7 minus 5 gets me back to 2 again, then plus and minus, addition, subtraction, are inverses of each other. These two, as you're going to see, although it's not obvious just to look at them, are inverses of each other. So that's what the relationship is between the two of them. So let's go over, first of all, down here at the bottom, let's go over the forms. Exponential form is, it doesn't have to be 10, it often is, but does not have to be. It can be any number with an exponent variable, with a variable in the exponent. So 10 to the x equals y is exponential form. 10 is called the base, x, as you know, is called the exponent, and this would be the answer. Now that same equation in logarithmic form is log base 10, so over here 10 was the base, here 10 is the base also, y equals x. What this is really saying is, what exponent do I have to raise 10 to get this y, to get this y? And the answer would be x. So let me write a number example here. Log Okay, so what this is saying, the way to read this is, what exponent do you have to raise 10 to get 100? So you'd have to raise 10 to the second power. That's the exponent that you would have to raise 10 to get 100. So 10 to the second power gives you 100. So it's kind of, it looks like it's kind of backwards and mixed around, but that's what a logarithm is saying. All right, so how you switch between the two down here, if this is an exponential form, the way I remember it is you make the base small and switch the other two. So you make this a becomes small. You got to put the word log on first. I should have added that. So you make the a small, so it's log a, and then the x and the y switch places. The y comes over here, the x goes over there. Okay? So that's how you get from exponential to logarithmic. From logarithmic to exponential, it's the other way. You make the base big, you take off the log also, the word log by the way. You make the base big and switch the other two. So the x and the y switching. So that's how you would switch back and forth between those. Okay, let's go ahead and go over some of the principles here. And they may not make a lot of sense while we're just reading them, but once you start applying them, they'll start to make more sense, okay? So let me talk first though, why do we use logs? Logs do two things. They straighten out a curved graph. Exponential graphs always are curved. They always have curves. When you take the log of that, you'll find that the curve goes away. It becomes a straight line. The other thing it does is it brings the range of values that you get for output from some really large number that you can't possibly graph down to a smaller, more manageable number. Let me give you an example of that. Okay, so let me give you an example here that comes from my AP Chemistry class where I teach this. So logarithms serve two main functions in science. They linearize, that is, make a straight line out of curved exponential functions so that analysis becomes possible. Second, they scale down outputs of an exponential function to make graphing possible. So let's look at a couple of functions here. There's a basic exponential function there, y equals 10 to the x power. And if you go ahead and do a t-table on that and plot those points, at 0, 10 to the x, 10 to the 0 would equal 1. Anything raised to the 0 power equals 1. At 1, 10 to the 1 would equal 10. At 2, 10 squared would equal 100. At 3, 10 to the third would equal 1,000, and so forth. So you notice when our domain is simply 5 numbers from 0 to 5, the range goes all the way from 1 to 100,000. Imagine trying to graph that on a piece of graph paper. You couldn't. 1 to 100,000 is too broad a range to graph practically. So that's one of the things that an exponential will do. It grows very, very quickly. Now let's look at this over here. This is a graph not of 10 to the x, but of the log of 10 to the x. So instead of graphing y equals 10 to the x, you're graphing y equals the log of 10 to the x. And what that gives you is, and you'll learn how this works when you plug in x, how you get those values. But if you put 0 in for x, you'll get the log of 10 to the x would be 0. If you put in 1 for x, you'll get y equals 1. 2 for x, y equals 2. So notice, I think a lot of you looking at these numbers could tell that that's a straight line. 0, 0, if you plotted that, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. It would be a straight line with a slope of 1. It would just be going upward from left to right with a slope of 1. But the other thing you notice, not only is it a straight line, but look at the y values. Instead of going from 1 to 100,000, they go from 0 to 5. That's very easy to plot that. So that's the two advantages of logs, is they turn a curved line into a straight line, and they give you an output of y that's manageable so you can actually graph it. Let's actually look at the graph of these two. So there's a graph right there. So graph y equals 10 to the x. If we plot an exponential of the graph, if we plot an exponential, rather, the graph will increase so quickly that it will not fit on a piece of paper. It also produces a curved line. So if you look at this, by the way, from 0 to 10 on my computer screen, you may be looking at it on a cell phone or a smaller computer. On my computer screen, 0 to 10 is about 1.5 inches. So if you extended that graph all the way up to x equals 10, that is y equals 10 raised to the 10th power, the red line would reach beyond the moon. That's how fast that line would grow. That's crazy. It's hard to believe that's true, but it is. So the red line would go beyond the moon. So you can't reasonably plot exponentials beyond about the second or third or fourth power before you go off of your graph paper. Now if we look at the plot of the other one, y equals log of 10 to the x, you're plotting x against the log produces numbers that can easily fit on a piece of graph paper. It also linearizes, that is, creates a straight line of the data. So unlike the graph on the left, this graph can easily display x equals 10. X equals 10 would just be y equals 10. And so you can easily plot that. So it's a straight line, and it's a small enough range of numbers that you can put it on graph paper. Alright, so let's continue on. Let's go over these principles kind of quickly, and then we'll get right into applying them to some actual problems, and you'll see how they work. So any number raised to the first power is itself. That's called an identity. So a to the first power equals a. 2 to the first power equals 2. 32 to the first power equals 32, and so on. Any number raised to the 0 power is 1. It's not 0, it's 1. The exception is 0. 0 raised to the 0 power is undefined, so you can't do that. Okay, the next few are some that we've worked with already. If you have a base a, so that could be a 10, it could be a 2, it could be whatever you want it to be. It's just that a and a have to be the same number. So a raised to the x power times a raised to the y power equals a to the x plus y power. If you have a raised to a power, and then you take that number, whatever you get from that, and then raise that to another power, then it will equal a raised to the x times y power. If you have a to the x divided by a to the y, you have a to the x minus y. So if you're multiplying, it's x plus y. If you're dividing, it's x minus y. Number 6. That's one that you've dealt with already. If the base and the exponent are the same, then you can add. So you've already done this in the last few units. You all know that 5x squared plus 2x squared equals, the x squared stays the same, and you just add the coefficients. 5 plus 2 is 7x squared. Okay, that's what that one is. Okay, this one, a to the minus x equals 1 over a to the x. So, in other words, 2 to the negative third power, that's equal to 1 over 2 to the positive third power. And that would be 1 over 8. Let's see if I squeeze that in right there, 1 over 8. Okay? You can also do it with the negative on the bottom. If I have 1 over 2 to the negative second power, that would equal 2 to the second power. I bring it from the bottom, from the denominator up to the numerator, so that, and you change the negative to a positive 2. So it would be 2 to the positive second power, and that would equal 4. All right? The n root of x equals x to the 1 over n. So if I'm trying to find the cubed root of 8, that's the same as saying 8 to the 1 over 3 to the 1/3 power. And in both of those cases, that answer would equal 2. All right, so cubed root of 8 is the same as 8 to the 1/3 power. All right, come on up here. Log of a plus log of b equals log of a times b. You know, you can test these out if you want with a calculator. It's just play around with them. Get a calculator with a log function. Find out what the log of a is, write it down. Find out what the log of b is, write it down. Add those two numbers together. Then come over here and take the log, multiply those two numbers together and take the log of whatever you get for that, and you will get the same number on both sides. So you can kind of prove these to yourself by plugging in some actual numbers. Okay, log of a minus log of b is going to be log of a over b. This is one that comes up in problem solving a lot. It's this one. The log of a raised to some power x is what you can do is, and it doesn't just have to be a single variable x. It could be 2x plus 4. It could be anything you want. It could be x squared minus 2x plus 6. It could be anything you want it to be. You take this exponent and move it out in front. So it's x log a. So you'll use this one somewhat often when you're solving problems. Now there's a different kind of log we use. Usually we deal with base 10. We're used to dealing with base 10 numbers. And that's just the standard number system that we use. But there's something in nature called a natural log, and it has a special number. It's called Euler's number, 2.718. It actually should be an 8 on the end there, although 2.71 is good enough. All right, and Euler's number is one of those magic numbers in nature, just like pi is 3.14159 for pi. Euler's number is this number. You know, don't ask why it's that number. Nature just decided that's the number it was going to be. All right, now the log to the base of e. The only two types of logs that we're going to be doing is base 10, and every other type of log up here, if it doesn't say a base, I should have mentioned this, it means it's base 10. Or you could say log to the base e. Again, the base can be anything you want it to be, but we're only going to deal with 10 and e represents that number right there. So the log base e of a equals the natural log. So they decided to give it its own designation, its own name. Rather than saying log base e, you say ln. Natural log is basically what that stands for. So log base e of a is equal to ln, natural log of a. All right, change of base. And this applies to either type of log. This is kind of a neat principle. It says that if you have a log of some quirky base that you can't do on your calculator, let's say it's base 7, 11, and you're trying to figure out what that is. In other words, what exponent, what power would you have to raise 7 by to get to 11? There's no way you can do that on your calculator. Your calculator, typical calculator, only has logs right there. Only has logs and natural logs. Okay, 10 to the x and e to the x. So that's the only one. You can't do just any base that you want on a calculator. But this formula allows you to. And it says that if I have log of base 7, argument is 11, I can come over here and put the argument on the top and the base on the bottom, and I can make that log to the base of anything I choose it to be. So that b is whatever you want it to be. So I'm going to come over here and I'm going to write it over here. Log, the 11 goes on the top, over log, the 7 goes on the bottom. And then you get to choose the base b. Well, what base would you obviously like to choose that your calculator can do? You could choose anything you want, but you're going to go ahead and choose base 10 because your calculator can do base 10. So now this strange problem that we wouldn't have been able to solve on the calculator, with the change of base rule, you can do it. Alright, so it would be log base 10 of 11 divided by log base 10 of 7, and that would give you whatever this is. Alright, inverses. Inverses, we're going to work with those, so it just says, since a log and an exponential are inverses, they undo each other. So if you take 10 and raise it to a power, that means it's an exponential, and that power includes a log in it. The exponential and the log are going to cancel each other out, and you'll just end up with this, with the x. Similarly, if you take an exponential function 10 to the x, and then take the log of that, it'll reverse it. The exponential and the log will inverse or reverse each other, and you'll get x again. And you can also use, and I need to change this, this should be ln. You can also do the same with e. E to the ln x equals x, and the natural log ln of e to the x equals x. Those are inverses. You'll see how those work on a problem set. Okay, so let's go ahead and get started with problem set number 4.01. So this is 4.01. I'm going to do the A problems and maybe a few of the others, and then you're going to do the ones that I don't do. All right? So here we go. So we'll refer to our principles as we go along. So anything raised to the first power is just itself. So 3 raised to the first power equals 3. Okay? You can go ahead and do this one. All right, next. 8 to the 0 power. Oh, we come over here, and anything raised to the 0 power equals 1 except if a equals 0. Then it's undefined. So right here we have 8 to the 0 power equals 1. Okay, over here we have 0 to the 0 power, and that equals undefined. It's the only one that you can't raise to the 0 power. Don't ask why, you just can't, okay? And now you do this one. Alright, next up. 2 to the second power times 2 to the third power. Don't just give me a number answer. Go ahead and set it up according to the rules here. So a to the x times a to the y equals a to the x times a to the x plus y. Number 3 here. So 2 to the second times 2 to the third equals 2 to the 2 plus 3, which equals 2 to the 5. Okay? And if you want to write the answer, it's 32. So come up here, you can prove that to yourself. 2 to the second is 4. 2 to the third is 8. 4 times 8 is 32. So you get the same answer as when you do it, go in this way. All right? This is an error. It's one of the reasons why you should watch these videos, is I can correct errors. And this one's going to be a 2. All right? So 3 to the 0 times 3 to the first is going to be 3 to the 0 plus 1, which equals 3 to the first, which equals 3 to the first, which equals 3. Okay, check it out here. 3 to the 0 is 1, and 3 to the first is 3, so 1 times 3 equals 3. Okay, again, change that A to a 2, and I'm going to leave 3C and 3D for you to do. And just follow the same rule. Okay, here we go. A to the third, and then raised to the fourth. So that's going to equal, we come over here, and the rule is a to the x, and then raised to the y is a to the x times y. So that's going to be a to the 3 times 4 equals a to the 12th. Okay. How about this one? 2 to the second and then to the fourth equals 2 to the 2 times 4 equals 2 to the 8th. And 2 to the 8th power, I can tell you, is 256. How about this? 2 to the second is 4. Go onto your calculator. So 2 to the second is 4. And then if I take 4 and raise it to the 4th power, that's also going to give you 256. So again, you can just plug in numbers for variables and test out to see if these principles hold. Okay, I'm going to leave number 4C for you to do. Okay, next up. A to the 4 over a to the 3. So anytime you have a division, a to the x over a to the y is a to the x minus y. So this one is going to be a to the 4 minus 3, which is a to the 1, which is a. All right. On all of these, just show one step of work, even if you can do it in your head. Give me a step of work. Don't just write down an answer, okay? That's kind of no credit for that. I want you to show just the step. Okay. In the future, once we're past this lesson, then if you have problems like this, you can just do them in your head if you want. But for now, since we're studying this subject, show me the work that you get there. Okay, here's a tricky one here a little bit. So a to the 3rd divided by a to the 7th. So that's going to be a to the 3 minus, be careful, negative 7. It's not 3 minus 7, it's 3 minus negative 7. That becomes a plus, so I can write that a to the 3 plus 7 equals a to the 10th. Okay. I'm going to leave 5C for you to do. Okay, how about this one? 2x to the 4th plus 5. You did plenty of these in the last couple units, right? So 2 plus 5 is set. As long as the base and the exponent are the same, you can add them. If either one of those is not the same, you can't add them or subtract them. So 2 plus 5 is 7. Not really possible to show a step of work here other than just write the answer for this one. So it's 2 plus 5 is 7, x to the 4th, okay? You do 6b. All right, 7a. There we go. Okay, I actually gave you the answer on that one. I'm supposed to have you write that, okay? So let's just write it. A to the minus 2 equals 1 over a squared. Okay, how about this one? 2 to the minus 3, you flip it and it becomes 1 over 2 to the positive 3, which equals 2 to the positive 3 is 8, so it becomes 1 over 8. So that's your answer. You do 7C. Okay, now we're going to get into some inverses. I did this one in class. I'll do this one as well for you, okay? I'm going to start way over here because I need some space. So, how do you get to that x? If instead of 3, this was 100, you could look at this and do it in your head. 10 raised to what power gives me 100? That would be 2. But it's not 100. It's a number that there's not a nice integer value for that. So 10 raised to what power gives you 3? All right. Since this number is less than 10, I'll just give you a hint. It's going to be a number less than 1. It's a positive number, but it's between 0 and 1. If it was 10 to the 1st, then this would give you 10. If it was 10 squared, it would give you a number bigger than 10. Since this is a number less than 10, then this is going to be a number less than 1. Okay, so let's go ahead and figure out what it is. So how do you do this? You use the inverse property right here. You have 10 to the x, so you take the log of that. And that'll undo the exponential. They'll reverse each other. So I'm going to take log 10 to the x, and that's legal. You can do that as long as you do the same thing to the other side. Log 3. Okay. Now, the next step you do is you recognize this principle, that log of a to the x equals x log a. So you can take that x out of there and stick it out in front of the log, okay? Again, don't ask why. It's just a principle of math. You go and study algebra in college, you'll go through all the proof that that's true, okay? But you don't need to know it now. So what I'm going to do is just take this and write it as x log 10. Go ahead and put the 10 in parentheses. You don't have to do that. Equals log of 3. Okay. Now I'm going to divide both sides by log of 10. This is just an algebra step. Why did I do that? Because these two now cancel out, and the only thing I have left is x equals log 3 over log 10. And that's what I want to solve. Alright, so I get log 3. I do that on the calculator, and that's going to give me, I'll show you how I do that. Okay, so I hit the log button up here, and then 3, and it opens up a parenthesis. It opens up a parenthesis, so I have to close that parenthesis. And so it gives me the log of 3 equals 0.477. Okay. 0.477 over the log of 10. So I come back here, and I hit log again, and 10, close the parenthesis, and that gives me 1. Log of 10 is 1. Why is that? Because log of base 10, 10. It's saying, what is the exponent that I have to raise 10 by to get to 10? The answer is just simply 1. Okay, so that's going to equal 1. So your final answer is 0.477. Okay? In other words, if I came up here and took 10 raised to that power, it would give me 3. Let's prove it. Okay, so 10, and how do you raise to a power? It's this little hat, or caret, okay? That raises to any exponent you want. And so you hit that, and then you're going to raise it to the 0.477 power. And we push it, and it's not exactly 3 because I rounded this number up here, the answer, but it's 2.999. That's basically 3, okay? So yeah, it works, all right? Okay, I'm going to do 8b. I told you I would do that one. So let's do it. What do you do? See, pause the video first and see if you can do it on your own. Remember, challenge yourself. Try to prove to yourself that you can do this on your own. Okay, so now I'm going to go ahead and do it. So it's log 2x equals log of 9. Okay. Again, I can bring the x out in front of the log. That's just one of the properties. And you just come over here and check around for all these principles. There it is right there. Okay, finally you divide both sides by log 2. And log 2 cancels on this side, so you have x equals log 9 over log 2. Let's go ahead and compute those. Okay, so log number 9, close the parenthesis, gives us 0.954. Okay, and log of 2, close the parenthesis, and that gives you 0.301. Okay, and now I go ahead and divide those. And that gives us 3.16. Okay, that's the answer. Let's test it. Let's see if 2 raised to the 3.16 will give us 9. Let's test that out. Okay, so 2. So you can see it. Then use the little caret here. And it's 3.16, and you raise it to that power, and you get 8.93. Okay, that's because I rounded down here. I rounded 2 numbers off pretty significantly. But yeah, it gets us to 9. It's good enough, okay? Now this one, I didn't leave you any space. You can just do this one up here, okay? Do that up there. You got plenty of space up there. All right, good. Let's keep going. Okay, next thing is this is another inverse problem. Log of 3x equals 2. How do you figure out what x is? You need to unwrap that x from the log there, okay? So how do you do that? Well, we have the other inverse principle that if I can take these two, and make them exponents of 10, so 10 to the log x, it's going to equal whatever that x is. So let me show you what I mean. So if I take 10, let me write it up here, 10, raised to the log 3x, that's going to equal anything you do to one side, you do to the other. So I took a 10 and I raised this to that, so I'm going to have 10 to the second. If these two are truly equal to each other, they are, then 10 raised to this power should equal 10 raised to this power if these two are equal. Okay, now what happens here? The 10, the exponential and the log cancel each other out, and all you end up here with is 3x. Over on this side, 10 squared is 100. So if you divide both sides by 3, you end up with x equals 33 1/3, or 33.3 is fine. Okay, so there's the answer. Again, if you want to play with it, go ahead and put it in the calculator and see. Okay, so that would be log of 3 times 33.3. And I'm going to close the parenthesis. And that's going to equal 1.999, which is 2. Which is 2. Okay, I did this one. I messed it up in class for 3rd period. So let's redo that. It's not that bad. Okay, so what are we going to do here? We now have a natural log. So we're not going to raise this. This one we raised to the 10 power because that was a log base 10. This is a log, natural log base e. So the way you undo that is you say e to the ln 2x equals e to the 7th. So the e and the natural log are inverses of each other, so 2x comes out. And e to the 7th, let me show you how to do that. Okay, so there's log, and there's 10 to the x above it. Here's ln, natural log, and e to the x above it. So I need to raise e to the 7th power. So that's the secondary function, the light blue function. So I hit second button, and nothing happens on the screen yet until I hit ln. And what it's really giving me is e raised to a power. There it is, e, the little hat, caret, raised to some power. And in our case, we want it to be 7. Don't forget to close the parenthesis. There's a parenthesis button down there. There's parentheses. Do that, and I click that, and I get 1,096. I'll round it to 1,097. That's close enough. Okay. Okay. Now I divide both sides by 2. I don't think this is a problem I messed up. That was a different one. Divide both sides by 2, so the 2's cancel. You get x equals that, which equals 1,097 divided by 2, and I get 548. You get some decimal places, but I'm just going to round it to 548, okay? There you go. Let's test it out up here. I won't put my calculator away because it keeps making it blurry. I'm going to do ln. Oops, I want to clear that. I'm going to do ln, what? Of 2 times 548. 2 times 548. Okay, it's a little glary here, but close the parenthesis, and that gives me 6.999, which is 7. Yeah, it's all rounded. It's causing that. Okay, let's keep going. Log of base 2 of 2 is simply log of any base of itself is 1. That's an identity. So these two are called identities because they return, in this case it returns itself. In this case you do a log against itself and it gives you a 1. Okay? Alright, next. So this one is going to be equals 1. Nothing much to show there as far as work. Okay, so you can do this one yourself. Next one, log of m plus log of n. That's just simply writing down what the property is. It's the log of m times n. Log of a plus log of b equals log of a plus b. So this is going to be log of m times n. Okay? Next one, log of m minus n. You come down here to this principle, and log of a minus b is log of a over b. Log of a divided by b. So this is going to be log of m divided by n. Okay? Again, you don't have to show any work there, nothing to show really. Okay, this one I'm just trying to get you to do the principle we actually did earlier here. This is simply going to equal x log a. You take the exponent and you move it out in front like that. Okay, it becomes x log a. You can do that one. There's no number answer to get. You're just rearranging it and showing how it works there. Okay, finally this one's change of base. So we'll do a couple of these together. I'll leave this one for you to do. So let's do change of base. So change of base says this, that right here, that log of x to the y is log of y over log of x to whatever base you want it to be. So this is going to be log of 5 over log of 3. And then the base you're going to put here, and here's whatever you want. We're going to go ahead and make it 10. Okay. So let's do that. Log of 5 base 10. So that's just what your calculator's calibrated for, log here. So log of 5 is 0.699. Over log of 3. Come up here, try to get it so you can see it. Close the parenthesis. I did close parenthesis on the last one. It still gave me the correct answer. It'll do that sometimes if it's a simple equation, but if you forget on a more complicated equation, it can really mess you up and give you the wrong answer. But be sure you close your parentheses. Okay, and that's 0.477. We've done that one before. Okay, so I divide these two. And I get 1.47 or 1.46 is good. Okay, so that's what you could not solve on your calculator because there's no base 3 to use. You couldn't solve that, at least on most calculators there's not. You can use the change of base to get that, okay? I'll go ahead and do this one. Log 6 over log 2. The base is going to be 10. And I won't put my calculator on the screen this time. And that's going to be 0.778. By the way, this thing that I'm doing, I don't know if I explained it to this class. I explained it to my science classes. It's called a leading zero. You don't have to put it there, but it makes it clear that there's a decimal point there. That's not just a speck on the paper. And it's just the way traditionally you write numbers properly is with a leading zero there, not just 0.77. Although it's not wrong if you did just write 0.77. Okay, now we're doing log of 2. Trust me, I'm doing it over here on my calculator, and I got 0.301. And if I divide those, I get 2.58. Okay, and I'm leaving 14C for you to do. And that takes care of the first assignment. I tell you what, we're at 38 minutes, so I'm going to stop. I'm going to do the second assignment on a separate video. So let me go ahead. I'm going to cease this one, and we'll go on. And the second assignment's pretty quick. It'll be very, very quick. I just don't like to go too much past 30 minutes, and I already have. Okay, so I'll see you on the next video.